So far we've been representing our complex numbers in Cartesian form, that's the form x plus I, y. But we can also represent our complex numbers in polar form, so that's the form r cos theta plus I sine theta. So this here on top is Cartesian form. This is polar form, and we can also represent our complex numbers in Euler form, re to the I theta. So this is Euler form. Alright, where r represents the modulus of your complex number and theta represents the argument of your complex number. So r and theta are modulus and argument respectively. So say for example we have in Cartesian form we've got the complex number 1 plus I. To represent it in either polar or Euler form, we first have to find r, the modulus, as well as its argument. So the modulus will be 1 squared plus 1 squared, so this is the square root of 2. And then to find the argument, let's draw it on a complex plane. This is the imaginary axis and this is our real axis. So we're moving 1 unit in the real axis and 1 unit in the imaginary axis. So I, and this is going to be our complex number. Alright, so if we look at our right angle triangle, the distance traveled in the imaginary axis is 1 and the distance traveled in the real axis is also 1. So the argument theta is going to be arctan of theta is arctan of 1 over 1, because opposite over adjacent, and arctan of 1 over 1 gives us a quarter pi. So it means if you're writing this in polar form, it's going to be the modulus, which is root 2, times cos theta, which is a quarter pi, plus I sine a quarter pi. And this would be identical to, if you're writing this in Euler form, that's root 2 e to the I a quarter pi. Alright, now before we look at some past paper examples of polar and Euler form, there are some rules for calculating modulus and arguments that I want to introduce. So let's say we've got two complex numbers, z1 and z2. If you multiply these two complex numbers, the modulus of z1 times z2 can also be represented as the modulus of z1 times the modulus of z2. And if they are dividing, so the modulus of z1 over z2, this would be the modulus of z1 divided by the modulus of z2. And for argument, for the case where they are multiplying, the argument of z1, z2 would be equal to the argument of z1 plus the argument of z2. So this is similar to that law of logarithms that says log AB is equal to log A plus log B. In fact, your arguments behave similarly to logarithms. And so for this case where we're dividing, arg z1 over z2 is equal to arg z1 minus arg z2. So these ideas tend to be useful when we're solving some questions on polar and Euler form. So let's look at some past paper questions. So we're given that the complex number u is given by u is equal to -1, -I root 3. Part A says express u in the form r cos theta plus I sine theta. So express it in polar form where r is greater than 0 and theta is between -pi and pi. Give the exact values of r and theta. So our complex number is u is -1, -I root 3. So we need to start off by finding our modulus r. So r is -1 squared plus negative root 3 squared. Alright, so we get that r is equal to, let's punch this into the calculator, that's the square root of negative 1 squared plus negative root 3 squared, and that gives us 2. And we also need to find theta. So to find theta, let's draw a complex number on a complex plane. This is our imaginary axis and this is our real axis. So our complex number moves negative 1 units in the real axis and then negative root 3 units in the imaginary axis. So that's almost negative 2 units. So negative root 3i. So it means our complex number would be somewhere here. And we want to find its argument. So the argument is the angle that it forms with a positive real axis. So we can draw a triangle, and let's call this angle alpha. We know that our opposite here is going to be the distance traveled in the real axis, that's 1 unit, and our adjacent is going to be the distance traveled in, there should be a right angle here. Our adjacent is the distance traveled in the imaginary axis, that's root 3. So we can say tan alpha is equal to opposite over adjacent, so 1 over root 3. So it means that alpha is equal to arctan of 1 over root 3. So alpha is equal to, let's punch this into the calculator, that's arctan of 1 over root 3. That gives us 1 over 6 pi. Alright, but we also have 90 degrees. So this part over here is 1 over 6 pi. So we're going to have to add pi over 2 to get the full red angle. So that's 1 over 6 pi plus pi, or 1 over 2 pi. That's 1 over 6 pi plus 1 over 2 pi. That gives us 2 over 3 pi. But notice that our argument is below the real axis, so it's going to be negative. So it means theta is negative 2/3 pi. And so if we're writing this in polar form, it's going to be 2 times cos negative 2 over 3 pi plus I sine negative 2 over 3 pi. Alright, and this would be our final answer. And now we're given that the complex number v is given by v is equal to 5 cos 1 over 6 pi plus I sine 1 over 6 pi. Part B says express the complex number v over u in the form rei theta, so Euler form, where r is greater than 0 and theta is between negative pi and pi. Alright, so this is where our laws for modulus as well as arguments come in. So to be able to represent v over u in the form rei theta, we first have to find r, the modulus, as well as theta, the argument. So the modulus of v over u, using our laws from earlier, can be written as the modulus of v over the modulus of u. So the modulus of v over u is going to be equal to the modulus of v, we can read it off here, is 5. So 5 divided by the modulus of u. The modulus of u is 2, so 5 over 2. So it means that the modulus of v over u is equal to 5 over 2. And then we also want the argument of v over u. So arg v over u is equal to arg v minus arg u. So arg v is 1 over 6 pi. So this means arg v over u is equal to 1 over 6 pi minus arg u. Arg u is negative 2/3 pi, so minus 2/3 pi. And so we get that arg v over u is equal to 1 over 6 pi plus 2/3 pi. So that gives us 5 over 6 pi. And so it means that therefore v over u can be written as r, which is 5 over 2, e to the I theta, which is 5 over 6 pi, 5 over 6 pi, and that will be our final answer. Alright, so let's look at this example. We're given that the complex numbers z and omega are defined by z is equal to 1 minus I and omega is negative 3 plus 3 root 3I. Part A says express z omega in the form a plus bi, where a and b are real and in exact surd form. So z omega just means we are multiplying our two complex numbers together. So that's going to be 1 minus I multiplied by negative 3 plus 3 root 3I. And so z omega is equal to 1 times negative 3, that's negative 3, 1 times 3 root 3I, that's positive 3 root 3I. Then we've got negative I times negative 3, positive 3I. Then we've got negative I times 3 root 3I, that's negative 3 root 3I squared. So z omega is equal to, we know that I squared is going to be negative 1, so this becomes positive 3 root 3. So it means we've got negative 3 plus 3 root 3 for our real part. Then for our imaginary part, it's going to be 3 plus 3 root 3 I. Alright, and so that's going to be our final answer. So now let's move on to part B. It says express z and omega in the form rei theta, so Euler form, where r is greater than 0 and theta is between negative pi and pi. Give the exact values of r and theta in each case. So let's start with z. Let's find the modulus of z. So the modulus of z is going to be the square root of 1 squared plus negative 1 squared. So the modulus of z is equal to root 2. And we also need to find the argument theta of z. So to do that, let's draw a diagram. So we've got our imaginary axis, and we've got our real axis, and z is 1 minus I. So 1 unit in the real axis and negative 1 unit in the imaginary axis. So z is going to be here. Alright, so the angle that we want, our argument is going to be this angle over here. So if we complete the triangle here, we know that this is 1 unit in the imaginary axis, 1 unit in the real axis, and so theta is going to be negative because our angle is below the real axis. Arctan of opposite is 1, adjacent is 1, so theta is equal to negative 1 over 4 pi. So as a result, it means that z can be written as root 2 ei negative a quarter pi. Alright, so that's the Euler form for z. So now let's find the Euler form for omega. So we have omega is equal to, omega is negative 3 plus 3 root 3i. So negative 3 plus 3 root 3i. For starters, we need to find its modulus. So the modulus of omega is equal to the square root of negative 3 squared plus 3 root 3 squared. So the modulus of omega is equal to, let's punch this into the calculator, that's the square root of negative 3 squared plus 3 root 3 squared, and that gives us a 6. We also need to find the argument for omega. So to do that, let's sketch an Argand diagram. So we've got our imaginary axis, and we've got our real axis. And so we're moving -3 units in the real axis, so -1, -2, -3, and then 3√3 I units in the imaginary axis, so about 5 units. 1, 2, 3, 4, just slightly over 5 is where we're going to have 3√3 I. So it means our complex number omega will be here. So let's draw a line from the origin to our complex number. So the argument of omega is going to be this angle over here. So it means for starters, we first have to find this angle. Alright, I'll call it angle alpha. So let's draw a triangle here. This is a right angle triangle. The distance traveled in the real axis is 3 units. The distance traveled in the imaginary axis is 3√3 units. So alpha is equal to arctan of opposite over adjacent. So our opposite is 3 and our adjacent is 3√3. 3√3. So we get that alpha is equal to, that's arctan of 3 over 3√3, and that gives us 1 over 6 pi. Alright, but to get theta, to get the argument of omega, we also have to add this pi over 2. So it becomes pi over 2 plus 1 over 6 pi, and this should give us the argument for omega. So that's pi over 2 plus pi over 6, and that gives us that the argument of omega is equal to 2 over 3 pi. And so this means that omega in Euler form is equal to r, which is 6, e I, theta is 2 over 3 pi. And so these would be the Euler form versions of z and omega. Let's move on to part D. Using your answers to part B, prove that tan 5 over 12 pi is equal to √3 plus 1 over √3 minus 1. So √3 plus 1 over √3 minus 1 looks like it could have something to do with our z omega. Let's see if we can find the argument of z omega. So if we draw an Argand diagram here, we've got our imaginary axis, and then we've got our real axis. So in the real axis, we're moving by -3 plus 3√3, which is around 2 units. So I'll put it somewhere here. So 3√3 minus 3, I'm just going to write it this way since they have the √3 coming first there. And then in the imaginary axis, we're moving up by 3 plus √3 units. So that's approximately 8 units. 1, 2, 3, 4, 5, 6, 7, 8. So somewhere here is where we'd expect to have, let me label it on this side so we've got space. 3 plus 3 plus 3√3 I. And so our complex number would be here. So let's draw a line going to our complex number, and we want its argument. So this is a right angle, and we want to find its argument. We'll call that theta. So tan theta is going to be equal to our opposite, which is the height, 3 plus 3√3. I'll write that in reverse order. So 3√3 plus 3 over the adjacent, which is 3√3 minus 3. 3√3 minus 3. So this means that tan theta is equal to, we can factor out 3 in both the numerator and the denominator. So that's √3 plus 1 over 3 times √3 minus 1. So tan theta is equal to √3 plus 1 over √3 minus 1. Notice how we now have the right hand side of what we're trying to prove. Now we just need to prove that tan theta is the same as tan 5 over 12 pi. So we know that theta is the argument of z omega. So this is tan arg z omega, and this should be equal to root 3 plus 1 over root 3 minus 1. So what we need to find is the argument of z omega. And we can use the laws of arguments to find this and say that arg z omega is equal to arg z plus arg omega. This is why they say use your answers to part B. In part B, we evaluated these arguments, the arguments for both z and omega. So the argument for z was negative a quarter pi. So this becomes arg z omega is equal to negative a quarter pi plus arg omega. Arg omega is 2 over 3 pi. So plus 2 over 3 pi arg z omega is equal to negative 1 over 4 plus 2 over 3, and that gives us 5 over 12 pi. So it means arg z omega is 5 over 12 pi. So in this equation here, we can replace our arg z omega with 5 over 12 pi, so that we've got tan 5 over 12 pi is equal to root 3 plus 1 over root 3 minus 1. And we have proved exactly what they wanted us to prove. Alright, so that's it for the Euler form and polar form. Make sure to go through the quiz, and I'll see you in the next video.